Good evening, everyone, and welcome to the December meeting of the Ozaki Radio Club. Pat W9JI, President of the Ozaki Radio Club. And I'd like to welcome our guest this evening, Brian Page, N4TRB. And Brian's going to be doing our program this evening, and it should be pretty interesting. Looking forward to it. And the topic for Brian's presentation tonight is the Transatlantic Tests of the 1920s, which happened in December of 1921, 22, and 23, I believe. And it's kind of it's an interesting story, and I think it's very timely. And I know it's a combination of work in DX, some contesting, because it actually was sometimes thought of as one of the very first contests, and something to do with history, which many of us are interested in. So first, I would like to just say a little bit about Brian, some biographical information. Brian Page holds an MA in the History of Science from Virginia Tech and is retired after 39 years working as a systems engineer in the computer industry. He holds an amateur extra class license and an expired commercial radio telephone license from his days at a top 40 AM station. He now writes about the history of science and technology from his home near Atlanta, publishing articles in QST, CQ, AWA Journal, QCWA Journal, and other publications. Amateur activities include mostly QRP operating, particularly with digital and building devices, and he has a current project restoring a Heathkit SB104A, along with a power supply and its external VFO. And I'm assuming that's the Heathkit behind your left shoulder there, Brian. Yep. Okay. And Brian, I'll turn the meeting over to you in just a minute. We have started recording. And as far as questions and answers, do you prefer to have people ask questions during your presentation, or would you like them to wait until afterwards?
It might be best to wait until the end.
Okay. And then the way we structure our meeting, Brian, we do the program first, followed by our business meeting. The business meeting is usually about 15 minutes. And then we, after the business meeting, people that are interested in talking about something stick around, usually for an hour or so. And you are welcome to stick around and join us, or to leave during the business meeting and come back if you'd like to talk about the presentation. And often the topic of conversation is the presentation of the evening. So okay, you're welcome to do that, or we can just do question and answer and then leave it at that. So that'll be up to you.
Yeah, well, I'm certainly flexible, so just whatever works out.
Okay, very good. And with that, I'll turn it over to you, Brian.
Okay, yeah, really the title of this is 1921 Transatlantic Tests, the Shortwave Revolution. And it worked out really nicely because, as you know, it's 100 years. In fact, tonight is a very poignant night, being December 8th. But most of the other commemorations of the test have really focused on the station here in the States. And I'll be touching a good bit on that too. But I'm not in this presentation, I'm looking really at the wider picture. So without further ado, let's go further into this. And part of my thumbnail video, there we go. So anyway, every good story begins with a failure. And then the hero can overcome the obstacles and we can have a happy ending. And the 1921 Transatlantic Test really was no exception. Surprisingly, the whole idea of an amateur transatlantic test did not originate with the American Radio Relay League. It was the brainchild of Milton Blake Sleeper, the editor of the radio department of the magazine Everyday Engineering, and also a really big name in the radio world at that time. However, before the magazine could pull it off, they had to suspend publication. Sleeper, therefore, approached the ARRL to take over the test. So that original test was on the nights of February 1, 3, and 5, 1921, so very early in the year. Select US stations transmitted prearranged texts for reception by British amateurs. Now, as you probably know, While US amateurs have been relegated to the useless wavelengths, 200 meters and down, British amateurs had been allocated what was then considered prime frequency real estate in the 1,000 meter band. Thus, British amateurs had little experience with short waves, and their antennas and the receivers were not optimized for the 200 meter signals used by the US hams. Additionally, and probably even more importantly, British amateurs were plagued by harmonics from their commercial stations, plus their own QRN originating from poorly adjusted regenerative receivers. So the result of that February test was failure, abject failure. Of the 250 stations listening for the Americans, not a single one unequivocally copied a transmission from any of the 24 US hams authorized for the test. And as the QST writer observed in reporting the failure, quote, "We would bet our new spring hat that if a good US amateur with such a standard American regenerative set and an Armstrong super could be sent to England, reception of US amateurs would straightway become commonplace." And if you've seen the cover of the December QST, you know about the bet with that hat. So anyway, the ARL was conjecturing sending someone, and that's exactly what they did. But before we look at the test itself, exactly why were the longer wavelengths so favored? So without knowledge of the existence of the ionosphere, physicists were challenged to explain the success of Marconi's 1901 famous reception on Signal Hill, St. John's, Newfoundland, of that S signal, dit, from Poldhu in Southwest England. Although there had been early scientific speculation by Kennelly and Heaviside about the existence of a charged layer high in the Earth's atmosphere, the theory of surface diffraction prevailed. In a nutshell, it was known that light and acoustic waves would bend around a spherical surface. Snell's law, which is primarily used in optics for the design of lenses, shows that waves bend toward a region of higher index of refraction. And the surface of the Earth itself has an index of refraction, which is quite high, as does the atmosphere, with a decreasing index of refraction with altitude due to stratification of the air and the water vapor in the lower atmosphere near the ground. So the first guy to take a crack mathematically explaining the phenomena was Hector Munro MacDonald, a good Scot, of Cambridge University. He modeled the Earth as a sphere composed of a perfect conductor. So in this simple model, he showed that radio waves do bend around the surface of the Earth. And importantly, the longer the wavelength, the more strength they are able to retain as they bend. But this model was extremely simple. Next up was the Frenchman, Henri Poincaré, who refined the model. It was better in that it didn't show that radio waves could go completely to the opposite side of the Earth. However, his formula included a constant that could only be determined empirically, the rate of attenuation. And he didn't have that. So the matter wasn't completely settled. Another Cambridge physicist, John William Nicholson, took a swing at it. His paper on the bending of electric waves round a large sphere appeared in Philosophical Magazine in 1910. Nicholson's results are fascinating and a lesson in the way that science works. He incorporated empirical data to prove conclusively how and in what amount radio waves refract around a sphere such as the Earth. This was really good hard science. And the work also showed that, as everyone expected, the longer the wavelength of the signal, the greater the signal strength at the receiving end. However, and here's the really interesting part, Nicholson observed that his predicted signal strengths did not match experience, writing, "Diffraction must be a relatively insignificant agency and the success of experiments such as those of Marconi. Thus, diffraction could not be significantly responsible for long distance propagation. When it comes to diffraction, his mathematical solution was airtight. What he proved was that diffraction wasn't responsible for long distance propagation. Therefore, something else must be going on." So we have a mystery. And who are you going to call? How about the United States Navy? The Navy had a bunch of stations scattered around the globe with antennas and transmitters that looked like these from Key West and Arlington. For command and control, the Navy needed hard data on propagation. That task fell to the Naval Radio Telegraphic Laboratory at the Bureau of Standards, not yet the National Bureau of Standards. So this mugshot is running the show. His name is Lewis W. Austin, and his work cast a long shadow. Austin arranged for the station at Brant Rock, Massachusetts, to conduct sending tests on 80 kilohertz and 300 kilohertz with two Navy battle cruisers, Birmingham and Salem, in late 1909 and early 1910. To make a long story short, Austin developed an entirely empirical formula, taking into account the transmitted wavelength, distance between the transmitter and receiver, heights of the transmitting and receiving antennas, the current in the transmitting antenna. The result was a tidy little formula that reasonably matched actual practice and applied to the long waves used by the Navy with their several hundred kilowatt rotary spark transmitters. The Austin-Cohen formula told the Navy what they needed to know, and the fact that it described long wave propagation only implied that long wave lengths were superior. Now, amateur operators were off the air for the First World War, and afterwards the Navy didn't want them back on the air at all. However, Congress prevailed, the Navy relented, but amateurs were given the wavelengths 200 meters and down, since both mathematical analysis and empirical studies had shown that these high frequencies were useless for long-range communications. Which brings us back to the ARRL Transatlantic Test and sending one of our own to the UK. The US amateur chosen for this, shall we say, de-expedition was Paul F. Godley, 2Z Echo, one of the premier receiver designers in America. Famous for his Paragon RA10 regenerative receiver. Godley and his receiver were so famous that he acquired the nickname Paragon Paul, a name which stuck to him forevermore. When you take a look at the receivers, you can get an idea of why British amateurs may have lacked the skills to handle 200-meter reception. So here's an RA10 regenerative receiver as seen in the Boneyard at Dayton in 2007. And that $950 price is comparable to the cost of one in the 1920s. So let's take a peek at the insides. And this is just the tuning unit. It's a beauty, but look at the nested coils and all these taps, these very fine caliber or close together taps on the various rotatable coils. It's a real wonder. And keep in mind, this is just the tuning unit. So you have the units to amplify the signal. So the second attempt was planned for 10 nights in December 1921, 100 years ago, beginning on the 7th, so 100 years ago yesterday. So thus equipped with a Paragon RA-10 plus an Armstrong superheterodon receiver, Godley boarded Aquitania in New York Harbor bound for Southampton. At that point, fortune smiled on the endeavor. Before even leaving the dock, Godley met Harold H. Beveridge, RCA engineer and newly famous for inventing the Beveridge antenna. Godley and Beveridge hit it off, and as Godley reported, quote, "During the voyage across, what time was not spent sleeping found me either talking to Beveridge or in the radio room." Upon arrival in England, Godley was met by H.J. Tattersall, superintendent of the Marconi Company in Southampton, who shepherded Godley through customs with all of his equipment intact. Mr. Marconi and the company that bears his name should need no introduction. Marconi at that time, the company, was the world leader in wireless communications with its powerful long wave stations knitting together the far-flung corners of the British Empire. Marconi had a history of confounding expert opinions, and he took great interest in these amateur shortwave tests. And the Marconi Company was not alone. RCA had loaned some of its latest and greatest vacuum tubes for use with both Godley's receiving equipment as well as one of the transmitters back in the States. More on that later. So once clear of customs, Godley was whisked off to London, where he attended a lecture by John Ambrose Fleming, inventor of the vacuum tube, and other dignitaries, including Marconi himself. Though Godley reports receiving well wishes at every turn, he noted, quote, "I am quite certain there wasn't an amateur in all Britain who thought it could be done." Their skepticism was well-founded. The British hosts had arranged for Godley to set up his gear in the home of Frank Phillips, a radio engineer and noted amateur. Phillips' home was near London. And when Godley tuned up his receivers for the 200-meter band, he discovered, in his words, "And what do you suppose we found? Static, gobs and gobs of it, and harmonics, whole orchestras of them. Home was never like this. One could read nearly all the high power stations in Europe on or near 200 meters. Godley endured 5 nights of this and then called up Plan B, like James Bond, and headed for Scotland. Specifically, Godley selected the little village of Ardrossan, a few miles outside of the town of Glasgow. Here, the Marconi Company stepped in to help save the day, providing transportation, antenna wire, insulators, batteries, and much else. Godley arrived in Glasgow on the evening of December 3rd and quickly got to work, gathering supplies and moving all to Ardrossan. There, he and his helpers erected a 12 by 18-foot tent, all in a howling storm. Then, on December 7th, the day the test was to begin, and taking advantage of his shipboard encounter with Beveridge, Godley laid out a classic Beveridge antenna, 1,300 feet stretched out, pointing toward Chicago, supported by 10 2x4-inch posts, 12 feet off the ground. The Beveridge is a wonderfully directive and efficient receiving antenna. The directivity largely eliminates interference and static coming from any direction other than where it's pointed. That noise suppression function was important in these early days of radio when filtering was practically non-existent. In one case, Godley tracked 39 harmonics from one commercial station, plus the interference from poorly adjusted regenerative receivers, which were themselves miniature low-power transmitters. So what's inside the tent? Of course, the Adams, Morgan, Paragon RA10 regen. And it's important to note that it's not simply the fact of receiving the signals on the opposite side of the Atlantic from us, it's that they would have been able to be received with both a regen set and a super heterodyne set, which differ quite significantly in sensitivity and particularly selectivity. So there's the Adam Morgan set, the schematic, and a little bit of the picture from the tent. And also in the tent was the latest in receiver technology, the super heterodyne receiver invented by Edward Howard Armstrong. This thing's an amazing set. And if we look under the covers of this, it gets even more amazing. And I'm not sure why, but like even the heater of all the RF stages has a rheostat. So quite a few adjustments to make this thing work. And as well as the fact that the beat frequency oscillator was external. You just brought it near to the receiver in order to, I guess, demodulate the CW signals. Also, in that cold, windy, rainy tent was D.E. Pearson, the chief inspector of the Marconi Company of Glasgow. His function was as a check operator to keep everybody honest. And over here, you might note on the floor, that was the heater, the only heater they had in this little tent. So I think their weather was even worse than my 45 degrees that I have today, but it's probably a little warmer than your 19. So finally, this is the poignant part. 100 years ago tonight, finally at 1 a.m. on 8 December, all was ready, and Godley began searching for amateur shortwave signals. Then, in his words, quote, exactly 33 minutes later, the universe cracked wide open. In one magic moment, Scotland's erstwhile gloomy shores became a haven of rest. Muscle soreness, soul soreness, fatigue, and doubt vanished, and my unexpectedly difficult but insistent duty became a joy forever. Godley had caught a station signing 1 AAW, running a synchronous spark transmitter, rag chewing with an unheard station. The storm still howled, and eventually the signal disappeared. That's when Godley discovered that his antenna was down. One pole broken and the other scattered out of line. In any event, at 6 a.m., Godley and Pearson pulled the plugs after 21 hours of work and headed to the hotel for a bit of rest. Testing continued for the next few nights. On the 10th, they heard station 1 BCG for the first time. 1 BCG was specially provisioned for the test and will be described in detail later. Conditions rocked on the nights of the 10th, 11th, and 12th, with dozens of stations heard and 26 logged. The vast majority of the transmitting stations were using CW, that is, vacuum tube oscillators. And as you undoubtedly know, CW packs all the power into a very narrow bandwidth compared to Spark. Still, a few Spark stations were received and logged, even with their inefficient and bandwidth hogging signals. Station 1 BCG was the powerhouse signal, and Godley noted, quote, the most remarkable feature was the strength of some of these signals. 1 BCG signals could have been heard easily 400 feet from the tent. Godley and Pierce considered confirming this speculation, but were deterred by the Scottish weather. Signal strength likely made a big impression on Pearson of the Marconi Company, especially once he found out that 2 of the CW stations were running less than 30 watts. Godley comments that Pearson was convinced that one BCG was running several kilowatts. Recall that successful reception involved copying prearranged 5-letter code groups like LXCAM. Godley did that, as Pearson confirmed, but the crowning achievement was copying the first standard traffic message to cross the Atlantic Ocean. And as you might know, in the early years, the American Radio Relay League was all about passing traffic messages. So number 1, this is 1 BCG, words 12, New York, date December 11, 1921, to Paul Godley, Ardross in Scotland. Hearty congratulations, Burghard, Inman, Grinnan, Armstrong, Amy, Cronkite. And it turns out that Godley and Pearson were not the only amateurs in Europe receiving the US signals. 1 BCG had been heard by 5 British hams, a Dutch amateur in Amsterdam, and by an American radio man aboard a ship in the harbor at Hamburg in Germany. If nothing else, the transatlantic test definitively showed the superiority of CW over Spark. Godley tallied the Spark and CW stations logged and noted, quote, "And glancing over the above list, one is struck by the preponderance of the CW stations and by the fact that the British heard CW stations only. This can mean only one thing, that CW is far superior, and I should like nothing better than to see all amateurs change over to continuous wave at once. Spark methods are horribly out of date and are so inefficient comparatively to be ridiculous, were it not that many have invested good money in Spark equipment." So the transatlantic test was successful, and Godley returned to the States a hero, his well-deserved reputation further burnished by this feat. But let's turn now to the other side of the ocean, to the station and the transmitter at 1 BCG. Recall that first formal message. It was signed by 6 individuals: Burghard, Inman, Grinnan, Armstrong, Amy, and Cronkite. The call sign 1 BCG belonged to Minton Cronkite. The Armstrong in that list was none other than Edwin Howard Armstrong, inventor of the regenerative receiver, the super heterodyne receiver, and FM radio. These guys were heavy hitters. Much of the coverage from that time centered on Paragon Paul and his Scotland adventure. But now I'm equally fascinated by the hastily constructed station 1 BCG located in Greenwich, Connecticut. The transmitter is a snapshot of 1921 state of the art. It was of a type known as a MOPA, Master Oscillator Power Amplifier, using 4 RCA UV4204 radiotrons, which had been loaned by RCA for the test. We'll see why in a few moments. 1 tube served as the oscillator over here at position A, and the other 3 were wired in parallel as the power amplifier B, C, and D. And power for the rig came from a 2,200 volt, 1.5 kilowatt generator with an AC drive. Interestingly, the oscillator ran continuously. Transmission was performed by 2 magnetically controlled keys, basically single pole, double throw. that fed the oscillator output to the power amplifier and simultaneously opened the grid link circuit. Altogether, the plate input power was about 990 watts, far, far from the several thousand watts suspected by Pearson in Scotland. And it was putting about 6 amps into the antenna for effectively 558 watts output power. It's no wonder that one BCG punched through so well to Paragon Paul in that little tent in Scotland. Looking at the schematic, you'll also notice there's no crystal. Crystal frequency control was not yet an established technology. The oscillator frequency was determined by the parallel LC circuit. And get this, also by the resonant frequency of the antenna. This is why a station's frequency could vary in windy conditions, which brings us to the antenna. Setup of the whole station was first begun on November 21st and completed on the 30th, just a week before the test was to begin. And I'm certainly envious of the station layout. The Radio Shack is directly beneath the antenna. And what an antenna. This is a Marconi T antenna. The vertical section isn't a feed line. It radiates, with the top horizontal sections forming a capacitance hat. And the bandwidth of Marconi T is rather narrow. In describing the station, George Burkhardt, one of the principals, noted that the natural resonant frequency of the antenna was 195 meters, close enough to their 230 meter signal that monitoring showed the frequency did not vary in the wind. They exercised as great care, knowing that an Armstrong superheterodyne would be on the other end. And in Burkhardt's words, quote, "A pure undamped wave must be used. It is obvious that the superheterodyne, with its great selectivity and highly resonant system, cannot give its maximum response when there is any discontinuity or variation in amplitude in the transmitted wave." They recognized that a stable CW signal was needed to stay within the selectivity passband of the godly receiver of the superheterodyne. Another aspect of their station that I love is the counterpose. At least 19 radials elevated, each 60 feet in length, extended from the top of the little Radio Shack. In his official report, Godley says, quote, "I took note too of the veiled interest which had been shown in engineering circles." Again, I think it was hardly veiled. Later, after the signals began to go in the log, he noted, quote, "Some radio history was being written in that miserable tent." We've seen that both the Marconi Company and RCA bent over backwards to give the test every possibility of success. For RCA, a success, no doubt, would promote sales of their tubes to the 20,000 American amateurs. Considering that the UV204 tube used in the one BCG MOPA sold for $110 in 1921 money, a little publicity certainly would not hurt. But much more was at stake for RCA than selling tubes to hams. In the same time frame as the Transatlantic Test, RCA was in the process of building a grand scale transmission facility at Rocky Point, Long Island, known as Radio Central. The plan was to install 12 massive low frequency antenna complexes, each consisting of 6 410-foot steel towers with 150-foot cross beams supporting 12 parallel wires, 7,500 feet in length. The operating frequency was 18.2 kilohertz. And the CW signal was generated by Alexanderson alternators. An alternator is just a motor generator that outputs a pure AC sine wave. 18.2 kilohertz is in the 16,500 meter band. It's like, how low can you go? But on the plus side, the Alexanderson puts out 200,000 watts. To say this sort of operation was expensive would be an understatement. RCA inaugurated Radio Central on November 5th, 1921, just a month before the amateur transatlantic test. You can see where I'm going with this. When President Warren G. Harding pressed the button set up in the White House, sending out the first message from Radio Central on that day, only 2 of the alternators and antennas had been built. Those 2 were the only 2 that were ever installed. In the years following Godley's success with shortwaves, RCA adopted shortwave, installing some 80 tube transmitters with power ratings up to 40,000 watts at Radio Central. 40,000 watts sounds like a huge amount to us, but consider that they were using Alexander alternators at 200,000 watts. Harold Beveridge, the RCA engineer who designed the receiving system for Radio Central, described the shift as the shortwave revolution. Marconi similarly adopted shortwave, indeed preceding RCA's deployment. Marconi progressively tested shorter and shorter wavelengths, finally settling on, you might guess, 32 meters in October of 1924, where he achieved successful 24-hour global capability. Another organization to take note was, as you might guess, the United States Navy. The Navy was in much the same situation as RCA and Marconi, running huge rotary spark exciters into giant antenna complexes. The cover of QST even has a little jab at NAA, the premier Navy installation in Alexandria, Virginia, just across the river from Washington, D.C., where they have Uncle Sam saying, "By gosh, I'll trade NAA for it," looking over Godley's shoulder, or I guess probably Milton Cronkite's shoulders at 1 BCG. So let's conclude with Beveridge's words. Quote, "So the shortwave revolution, as you might call it, really changed the whole picture of international communications. The 1921 Transatlantic Test had implications far beyond amateur circles, and that revolution began with Paragon Paul Godley and a little 12 by 18 foot tent pitched in a freezing gale on the coast of Scotland." So I guess let's unmute everybody, and I'll maybe even end this.
And since I've got the microphone, I will ask the first question.
Okay.
I found the coincidental meeting with Beveridge to be very interesting, and just wondering what your opinion is, Brian, on how much that played into the success of the overall mission, since it seems like the Beveridge antenna had to be critical for Godley's installation in Scotland. So what if he had never met Beveridge, or what if Beveridge would have been on a different ship?
Yeah, I mean, that is interesting. My initial inclination was to think that Beveridge probably saved the day. However, you do have to take into account that I believe it was 6 other British stations also received those CW signals. So perhaps not, but you know, Godley, if you read Godley's account, he goes on and on and on about how much interference they were receiving. They just didn't have the filtering. They didn't really even have necessarily the concept of the filtering that we have today. So yeah, it's hard to say, but I think it contributed in great measure to the success.
Okay, interesting. Well, thank you. And for those that are interested, you can search up the 1923 Montgomery Ward catalog on the internet. And on page 11 is the Paragon detector amplifier and the Paragon regenerative tuner. So if you want to see what those look like, and the ad copy is very interesting to read. Not entirely correct necessarily, but very interesting to read. Do we have a question for Brian?
Yeah, I have a question.
Tyrell, go ahead.
Yeah, I was kind of curious. So what was the difference in Britain versus America? Why were they having so much interference on the 200-meter wave band versus here?
Yeah, that's actually a pretty good question, but I think it probably has to do with just the compactness of the European landscape. So you had so many stations, crowded together.
Was that like commercial radio stations or like power stations, or what was causing the interference?
Yeah, it was commercial stations.
Oh,
mainly.
like radio. Okay.
Yep, commercial traffic stations.
My question is, since this was one-way communication, when did they finally have some two-way success?
I should probably know that, but I believe it was 1923. One of the problems is the British amateurs were not licensed to operate on those frequencies, so it was illegal for them to transmit. They were also limited, even though they had the prime frequency real estate in the 1,000-meter band. They by law, their antennas were restricted in length, so they couldn't even have a decent antenna for the frequencies that they were allocated.
When did that change? I mean, when did they get more like the higher, lower, whatever, the other frequencies?
Yeah, I'm not really sure.
Oh, okay.
Yeah. My interest at this point is discovering exactly why long waves became the de facto standard. As we talked about with the Austin-Cohen formula, his formula applied to the long waves because that's what the Navy was using. But it was taken to mean that long waves were the best. And they didn't really look beyond that, at least until, this test came along, and then particularly Oliver Heaviside and Kennelly, conjectured the existence of the ionosphere and then later proved it.
I have a question.
Go ahead.
Yeah, I found it interesting how the different companies were giving support, like RCA and Marconi. Now, you mentioned RCA had something to gain by, selling tubes to hams. What was Marconi's thing in this? I mean, I would kind of think they might have looked at this as sort of a threat at some point.
Yeah, well, not really a threat. Is really just RCA. I don't think was that convinced that they were going to be selling tubes to amateurs that cost over $100 in 1921. That's probably that could be a year's salary for some people at that time. The motivation was the hugely expensive rotary spark transmitters and the Alexanderson alternators. Those are, hugely expensive, not to mention the towers and stuff. So if the short waves, proved useful, then, being able to replace an Alexander alternator with a couple of vacuum tubes just was, you can't even, I think, underestimate the extent of the revolution that occurred, as Beveridge noted. The picture I showed of of Radio Central had that huge building with the fountain in front. That fountain was not just decorative. The fountain was part of the cooling system needed for the 200,000 watt transmitters that they envisioned having.
That's interesting.
Brian, just a couple of comments. I was going to say back to Gary that RCA had double interest there. Marconi was an international communication company, but RCA was too. They weren't just making tubes. They also had these transmitter sites.
Yeah.
So I suppose this conjecture would be that they were suspicious that the hams or this other group, these group of people were onto something. So they supported it because, as you said, they had a lot to gain if they could get rid of this really expensive equipment. I was going to also bring up the point. I did not realize until your presentation tonight that there was a super heterodyne receiver on that trip, because I'm really wondering now how long it was after that hams picked up on super heterodyne. The first really successful super heterodyne receiver, not that there weren't others before that, was National had the FB7, which was 10 years later, I think 1934. And they also had an AGS, which I'm not really sure was super heterodyne. But it was right at that same time frame. Anything you've picked up on the proliferation of super heterodyne radios after those tests?
Yeah, that's a really good thing to research. No, but I mean, people were still building regions into the 40s as their primary, and even commercially available into the 40s as their standard receivers. And
well,
of course,
those of us that were early in ham radio and bought night kits, those were all super regenerative even into the 60s.
Yeah, yeah. And you mentioned the RCA motivation as well. I mean, of course, RCA was created really at the behest of the United States government, because they, going into the First World War, they couldn't have a foreign company really supporting all the communications. So yeah, RCA was an intentional creation for primarily international communications.
Didn't RCA eventually buy Marconi?
The RCA bought out the Marconi properties in the United States, but Marconi is still a functioning company today.
Yeah, they bought out the transmitter, the communications arm, didn't they?
Yes,
they didn't buy out the radio making part of it.
Of Marconi. Yeah, they did not buy out the Marconi. You can see Marconi receivers and transmitters and so forth, but the shore stations in the United States went over as part of the creation of RCA. They went over from Marconi to RCA.
Right.
In the book Empire of the Air, there's a section on how the RCA company was created. I seem to recall that the U.S. government was going to nationalize the Marconi assets that were in the U.S. and then form the company. And I think they did pay them something for them, but it was rather a forced sale, if I remember correctly.
Yes, it was a forced sale. And we've run into that through quite a few different technologies, even up to the present day, where the United States government, particularly with the military, the DoD now, does not like depending on foreign companies for, let's say, business critical equipment and infrastructure.
Sorry, too many questions. But I guess when you say something interesting, you can expect people are going to have questions, right? I was just listening to that. You were talking about these kind of, ridiculously low frequencies, and obviously antennas that are huge and all that. And I mean, today we've still got 160 and 630 and 2200 that we can use. So obviously that changed, and people started moving towards, I guess, what we now call shortwave. But today, do people still use these really low frequencies, the high wavelengths?
Not the only, well, there's work with submarines that use those ridiculously long antennas, and the antennas are miles and miles long, and they're buried. Other than that, the only thing that I can think of are the the non-directional beacons that are used in aviation. Although I haven't seen a non-directional beacon receiver in a small airplane ever, but they are still out there.
So it's not very
there
common.
is a large array in northern Wisconsin, I think, that runs at something like 16 kilohertz or down there, and due to the depth of skin effect that's used to put signals into submarines that are actually submerged that can pick it up.
Yep. And of course, there still is one Alexander alternator going, it's on the air like twice a year.
Really?
Oh yeah, yeah. And one of my dreams is to set up a beverage antenna somewhere and receive it.
What frequency is that running at?
Oh boy. Somebody can probably Google it real fast, but
isn't that close to the frequencies, Gary? XT, isn't that close to the frequencies for our VLF allocation? You get involved in that.
It's like 13 kilohertz.
Well, I guess that's our
It's
allocation.
pretty low, yeah.
Yeah.
You'll see an announcement like in QST or something like
Right.
that.
Yeah, the station is SAQ.
I think they get on around Christmas time, so it might be worth
Yeah,
taking a look
it
in a
would be
couple of
about the
weeks.
right time. This is the time of year for all that stuff at those frequencies.
So I have one question. Well, first off, wonderful presentation. Thank you. So they're in Scotland and it's the 7th and they heard the station. Yay. How and when did the US know you've been heard?
Well, that's a good question. But what they godly would
Satellite
do,
phone, they just called them up.
Yeah, got the satellite phone.
they would communicate via commercial radio telegram. And in fact, it's this is kind of a funny story, a sad but funny story. At one point, once Godley had realized that the receiving was going very well, he composed a message that said, send message MSG, using an abbreviation for message MSG. And it got transposed by the operator who sent it. And it was addressed to like Burkhardt and that crew at 1BCG as send MGS. So 1BCG spent hours with a hand key sending the Morse code letters MGS over and over again. And what Godley was trying to do was get them to start sending regular traffic. So yeah, they kept up to date with each other through, on a daily telegraph message.
I believe it was the Marconi commercial wireless station that sent the telegrams back to the United States.
Yeah, because Marconi, of course, had a monopoly within the British Empire on long-range communications, or all commercial at that point.
And didn't Tesla bring suit against Marconi for taking some of his patents?
That's probably true. I'm not a big Tesla kind of guy, but he sued everybody. So yeah, I would imagine so. Tesla's a sad story, and a great deal of it was self-inflicted, and a lot of his technology is confusing to begin with. But there are people who are passionate about Tesla.
And Marconi had
Go ahead.
Marconi had multiple suits from a lot of other companies too.
Oh yeah.
And one question that came up in the chat was, what page in the 1923 Montgomery Ward catalog was I referring to? It was page 11. So if you guys want to look that up, it's kind of interesting looking at that old equipment.
I have a comment.
Go ahead, Stan.
Okay, I run the auction during the regular meetings, or I have in the past, and I get withdrawal symptoms. So I'm going to have another online auction pretty soon, and it's going to be largely books. And one of them is a book that was donated to the ORC called Drake's Radio Cyclopedia. And I've got it here with me now. It's a 1929 encyclopedia of radio terms and circuits. And it's largely for what we would call low band and AM broadcast band. It's a great big book, and I've read it cover to cover, and it's really a jewel. Somebody would like to have this for their own library. Drake's Radio Cyclopedia, 1929, by Harold P. Manley. And so keep an eye out, because we're going to have an online auction coming up in the next 2 weeks, and this will be one of them.
Okay, very good. Thank you, Stan.
Okay.
A tiny little bit of trivia, because we all look like we're the right age group here. Does anybody remember the boys' first book of radio and electronics? First book, second book, third book, and so forth?
Alfred P. Morgan.
Alfred P. Morgan. Yes,
I
indeed.
have a couple of them here.
Yep, I've got the whole set. Godley and Morgan were business partners. So the RA-10 regenerative receiver was a product of the Adams Morgan Company. So Morgan's call sign was 2Z Echo. So one dit away from Godley's of 2Z, he was 2ZI, and Godley was 2Z Echo. So they were business partners, but it turned out they kind of couldn't get along. So Godley bailed out of the company a little later on. But yeah, well, good old Alfred Morgan and Godley were all in on this, and that's where the receiver came from. Okay, sorry, Pat.
Okay.
Patrick?
Very interesting. Oh, go ahead, Tom.
What year of Montgomery catalog was that?
1923.
Okay, I'll go downstairs and see if I can find it.
Okay. Tom has that in his library, I'm sure.
It's the third pile from the left.
Tom probably bought it in the bookstore.
Maybe. Do we have any other questions for Brian?
Well, we were just talking about books. We got off on that subject, and I just finished a book called Thunderstruck by Eric Larson, and I just finished it a couple of days ago, and it really dovetails really nicely with your presentation, Brian, because it really documents the early days. Well, first of all, it's kind of a murder mystery and invention book, but it documents Marconi's early work. And he really faced a lot of uphill challenges, politically, financially. You mentioned the US absconded with some of his properties. Well, the Germans were trying to steal stuff too, because the armies figured out pretty quickly this was a big deal for making war if you could communicate. And so this book Thunderstruck is right around 1900, maybe a little bit after that, as Marconi went into his first transatlantic communication efforts, and they were unbelievably difficult. And I didn't realize the effort that went into creating those stations in some very terrible locations. So it was interesting. I'd encourage people to get a copy if they can. It's not a new book. I think it's been out for 10 years or so, but it's really, really good.
Okay. Well, thank you, Fred. And I see Peter holding up the boys' book of radio and electronics.
Yes.
And actually, one of the first conversations I ever had with Peter was on the design of the regenerative receiver that's featured in that book, and also on a popular YouTube channel. Interesting stuff.
When I was in fifth grade, a classmate and I went over. Well, we looked at this book. We didn't read it, but I really liked this book back in fifth grade. So I finally got it off of eBay a few years ago.
I think I kept that book checked out permanently for my entire fourth grade out of the school library.
My very first receiver was a homebrew 3A4 vacuum tube. It's a single tube, regenerative, and I suspect it came out of the QST, but I don't recall the source. But that was my very first receiver.
Interesting. Okay, do we have any more questions for Brian?
Yeah, and Pat, I think we've covered a lot of the questions. So probably I don't need to stay around through the business meeting and the chat rooms then.
Okay.
So, but it was wonderful having you folks as an audience. It's always nice to have, you know, a group of people who find this interesting.
Thank you.
Thank you.
Very nice job, Brian. Thank you. And I believe it was very interesting. And I do appreciate all the effort that went into putting it together, and you're taking time to be with us tonight. And one other interesting thing that I did come across in reading up on the transatlantic test was that the one BCG shack was actually moved to be under the antenna. So they didn't put the antenna up to be over the shack. They moved the shack to be under the antenna. And that's some dedication, I guess, to having some successful communications. So thank you very much, Brian. And you are certainly welcome to stick around. We'll have a brief business meeting, and then we'll talk for a while. And I'm sure there's many more comments and questions about transatlantic tests and early radios that'll be coming up. So let's.
But I think I'll go ahead and bow out. But yeah, thank you all for attending. I appreciate that.
Thank you, Brian.
Very good. Thanks, Brian.
Bye, everyone.
All right.